So during rebuild, yeah, I will introduce our next talk. Everyone looking for truly push their OpenStack cloud into high gear, please welcome Kritik Sachdeva, technical support professional at IBM. His presentation, The Need for Speed, addresses the biggest bottleneck in the cloud, the storage layer. The highlight, he will demonstrate in a live demo how to integrate external Ceph storage with OpenStack. Please welcome Kritik Sachdeva.
Hello everyone, good morning. Okay, so this is a topic I am going to cover that it's a POC that I have been created for integrating the NVMe-oF in Ceph for OpenStack, like if you are going to run your AI workloads in OpenStack. So let's start with a bit about myself. So I'm a technical support professional at IBM, and I try to explore like integrating multiple technology when done like that in my free time after that work. And I have also done certification of Red Hat, and I'm a RHC level 12. And by passion, I am an artist. So I do calligraphy and paper artist as well. So teaching like that. So if anybody interested, like want to me to write their names in their beautiful calligraphy, you can reach out to me. So let's do the agenda. So I will cover what basic storage gaps that we have in an AI pipeline, and like bit about Ceph and NVMe-oF, like basic introduction and how their architecture looks like, and then the POC demo that how the request flow works in OpenStack for the POC that I created, and with a demo video, and finally with the use case. So let's with the storage gaps. So as we have the AI workload that they are getting evolving, so the storage requirements is also need to be updated accordingly. So like this is a like basic evolution for the storage growth that we can have. Like in a very earlier phase, we have traditional ML. The data is very small, like we are using a random forest or any regression data algorithms in the AI. So data will not need to be much higher. So you can have a GB of data. But then now we have LLM, so it's having a petabytes of data. And after that, we have agentic AI, and now it's more moving toward the physical AI, where the AI will getting a knowledge about their physical awareness. So the data amount it needs to be trained on, or how much data it's going to be ingested, it's going to be very huge. So because this trend is going in the increase in the requirement for storage, so our storage needs to be grow as well in the for the AI pipeline to support that. So I just pick up one basic pipeline, like if you can think of a web DevOps pipeline, like simple one. So it will vary depending on the different type of ML workload that you're running and different type of application use. So like in the first phase, you have data ingestion. So most recommended storage would be object storage or data lakes. And if you are using data processing, recommendation would be to have a object and file storage to have a parallel operations. For model training, also we recommend to have file system, and for deployment, we mostly use VectorDB for LLM or inferencing of the database, and finally monitoring. So in the model training or model deployment, there are some things like in the model training, we have checkpoints. So checkpoint is a very heavy operation. It needs to store all the AI weights on the system before it move or resume the AI training process. So if the storage is slow, the GPUs are going to sit idle and they are not going to do any operation. So for that, you need to have a very high latency operation for the model training, where we're having a checkpoint need to be stored very quickly. And for model deployment during the inferencing, when we are using a RAG-based pipeline, the vector search is very latency sensitive. So that also needs to be very critically accordingly if we are depending on the RAG for the area. So these are the three considerations. Like because of AI, your data needs is growing. So for that, you need to have a storage solution which can grow. Higher performance also need for the AI workload. You cannot like GPU are increasing their power and they are getting very highly efficient. But if your storage is not getting cope up with that, it's gonna stay back. And same thing with the cost and scalability, how much you can scale, and like from the latency point of view, it's gonna cost also. So these are key considerations, and same reason just the modern workload required a storage that needs to be cope up according to the AI workload. So the training for the data set and checkpointing vector database, and sometimes if we are using any database for your AI analytics application, and that also you need a low latency database. So that's a very line. I think yesterday also we get to know about that. If your storage is not efficient or high IOPS or low latency, and your GPU are gonna sit idle. They are not gonna do anything. So let's talk about the Ceph and NVMe basic. So Ceph is like software-defined storage. It's very easily scalable, and it provides all three types of storage: RBD, block, Ceph for file, and object for S3 RGB. So that's, I'm not going to cover Ceph anything. That's a base introduction for Ceph. It's very scalable and flexible for you. And NVMe-oF TCP. Here I'm talking about NVMe-oF as a protocol, not NVMe-oF fabric gateway that we have in Ceph. So NVMe-oF is a protocol that is used in NVMe devices, which and to which we store the data in a physical device. But if we are going to extend that same protocol of storing the data that is used in an NVMe device over the network, then it comes under the category of NVMe over TCP. So it's a very simple modernized protocol that will be replacing the ISCOV for faster and better performance. So that's the NVMe-oF TCP protocol, and it's low latency, and it provides very high throughput and for the workloads, and it's right now it's industry standard and widely accepted. So let's talk about NVMe-oF gateway in Ceph. So it's a service which exposes the Ceph RBD image to the client via NVMe-oF commands in the TCP protocol. So it basically provides a block level access, and it's integrated with the Ceph idiom, so very easy to deploy. You can very quickly deploy it. And you can think of this as a, it's an NVMe-oF target and a Ceph client as well, because it's going to communicate with the RBD. So it's a Ceph client, and it's going to provide the storage to a client. So it's a target also for the, like, ISCOV we have. So it's like a translator between that. And we can very easily tune the NVMe gateway, like we can scale it up to, depending on the processor or cores or memory, you can very easily configure the tuning for NVMe-oF. So this is a very overall picture of how NVMe-oF gateway fits in the Ceph cluster. On the right side we have Ceph cluster, and left side we have the client, which the initiator. So let's some basic terminology in NVMe-oF gateway. So namespace is equivalent to like an RBD image, which is mapped to going to be connected to the client. So namespace is very equivalent to an RBD image. So it's like a LUN in that we have in ISCOV. NVMe subsystem, it's a entity which combines the namespaces, different multiple namespaces in a single subsystem, and it also has a controllers. And controllers is like it's a component which help to scale the client performance. Like you can, multiple clients can connect in the same subsystem for the NVMe. So single controller is going to connect it with the single client, and for multiple clients you can have multiple controllers. So it's going to be one-to-one connection, so it would be highly efficient performance. And it also provides an NQN, which is a access control to map to the client to access the namespace. Next is IO controller. It's created for every connection between the host and the target client, and it's for one initiator, only one controller it would be there, which is going to control all of the connections in that. And listener is like in a NVMe gateway, when we configure, we have to have a listener, which is a port on which the NVMe gateway is going to expose its service to the client. And gateway group is a like high availability feature in NVMe-oF gateway, where you can have multiple NVMe-oF gateways which are providing a active passive connection to the client. So this is all of these components. When we club them and put it in a picture, this is how it will look like. That NVMe-oF target is having a subsystem, and for each client there is a controller and having a namespace, and namespace is mapped to RBD image, and it's called to Ceph cluster. And for the configuration also, we are using a gRPC in the Ceph to securely configure all of the configuration in the NVMe gateway as per our need. And for multi-pathing and high availability, like we have multiple gateways and both are representing to the same subsystem, but on a two different nodes. So they are using a concept of ANA, like for which one is an active and passive to provide a high availability to the data. So this is about NVMe-oF gateway. Okay, so all the component that we pick up and all of that. Next is for the performance. I've picked up from the Ceph blogs that when we scale the NVMe-oF gateways with the cluster, the performance is also gets very easily scaled up. And if you look up in this diagram, there is one important factor that it's mapped to one block device. If it's mapped to one block device, you see the performance is getting very easily scaled up. So this is one concept that I used in my POC to when creating a OpenStack volume, that I mapped it to a single namespace, because in a single subsystem we can have multiple namespaces also, but because of the performance that we can get when we use one subsystem having a one namespace, that's why I created in a POC, so I can show it to you later. And same thing we can see in the different read-write performance, that it's very easy to scale. And this performance can grow more if you had more CPU or more performance in the nodes. So I did one simple comparison, like for RBD, if you are using for a vector database, if you are using a RBD image, and if you are using an NVMe-oF export image for that. So this is the results I get. It's a very basic one. It's because I'm not a testing engineer, I'm a support. So very basic testing I did for a vector search and vector insert operation. And for the vector insert, the basically write operation, at the backend we have RBD. So NVMe-oF write operation is depending on the NVM on the RBD. So that's a baseline for write operation. But for vector DB, like during the inferencing, we are not gonna write anything in the database. We are mostly going with the read operation. So read is the most important thing, and in the search query, if you see that NVMe-oF gives a much faster, like half of the latency operation, so the search operation. So this is one testing I did, and this is a baseline for RBD. For write operation, it's below because, and it's having an additional layer for because of NVMe-oF, but for the search operation, read operation, it gives a much higher throughput. So this is the one that I get, and this test I did for the 10,000 vector insert operation and 1,000 vector search operation. So this is the result I get. Let's start with the POC, like how the OpenStack connects with the Ceph NVMe-oF. These are the components like Cinder service, RBD, and NVMe. So I try to correlate with the diagram which request flow, how it goes. So at first I created a like normal in the OpenStack, we have created a volume. It uses the same RBD module to create an RBD image and provide it access to all of the metadata back to Cinder service. Then here I use the same protocol that we see in the initially, that gRPC protocol, which creates a subsystem and all of that. So I use the same concept here, that it's when I created a NVMe-oF volume, it creates a NVMe subsystem access control for that particular node, and it also exposes the namespace, that the RBD image that is created, it uses that same RBD image and exposes it in the namespace, and it provides all of the details back to the Cinder service. And till here, volume is created, but when we try to attach the volume to any virtual machine, it provides send all the details to a Nova Compute service, and that will attach the volume to the node and inside the virtual machine also. And finally, when the connection is terminated, initially I created it like when connection is terminated, it will destroy the namespace, subsystem, and listener, all of the resources. But later on, I felt that it might be better that because in AI workload, we might need to attach the same volume on the same node to a different application. So we might need to just attach it from one application to a different application. So in that case, recreating the subsystem and all of that resources may be irrelevant. So for that context, I made it like when we terminate the connection, it will only remove the namespace and it access control, but the subsystem and listener, they are stayed there as it is, because when we try to remount or recreate a connection, it will just recreate a namespace and just attach it to the. So it's just a saving time and any ops operation from doing any extra work over here. So let's talk a demo. Okay, so this is a demo I created. So I created one volume type that it's specifically for NVMe-oF, and it in the backend it's using an RBD, so which I mentioned in the configuration that when we create an NVMe-oF type protocol, which backend volume it's going to use to create a volume. So in the configuration, I mentioned that RBD NVMe-oF backend driver. So backend name is RBD. So that's how when we create a volume of NVMe, it will gonna create a RBD image first. So you can just check that there is no volumes at the Ceph layer. There is no volume. And before we go and perform any volume to install any volume creation, the NVMe CLI needs to be installed on the node that's submerged, because that's going to mount the connector to a NVMe device. So I created a volume with the type specified with the NVMe-oF. And the same time, we can validate from the RBD layer that it's created the volume. We can check the ID that it's created successfully. And this is one server that I kept running because I keep facing some issues with the server launching on that part. So I kept one running while recording this video. And this is one you can see that in this virtual machine, the device which is mapped on this device. So there is one image that is by default created when we create a virtual machine with the RBD image. So there is one device is there. So one is the VM, like default when we create a root disk for the virtual machine. Now I've added this NVMe-oF volume and on the server. Now if we run the same verse command, we can see that the NVMe connect is done, that the device is connected to this node, and we can also see that it's a new device that's also attached to the inside the virtual machine. And from the Ceph side, we can see the all the subsystems and all of that is created for this node specifically. It has created all of this very dynamically for the Cinder service. For a namespace, we can map the volume ID that was the same one that we see for the NVMe volume type that we created. And this listener IP is the host IP in which the virtual machine is running, where the NVMe connect command is running. So I'm going to retain the listener and the subsystem resources when the client connection is terminated. So because the same node can be reused, so I just don't want to do a redundant operation again. So just for that purpose, I kept it like that. Now if I just remove this volume, oops, sorry. So when we do the remove, it just removes the volume from the virtual machine, but it's still present on the node, because if I need to attach it to a different node, I will just do that. But so everything stays there as it is because it's attached. Now, when I delete this volume that I created, everything that it's connected on the node, it will get removed, and namespace at the backend gets removed. When we deleted the volume, it's removed the volume from the node, and finally we can see at the end that subsystem and listener is there, but there is no namespace. So that's it from the demo. So let's talk about the use cases. So one use case is like when you want to host your own vector database on the cloud for your internal application, like different AI pipelines. So that's the one use case where you're using a RAG, because right now RAG is a very common and very easy way to use AI in your pipeline and your any workload for your documents searching or any information extraction. So vector database is very easy to scale, like where we put data from PDF files or documents or emails or anything like that. We're going to put in the vector database for the searching operation or AI to integrate with that. So vector database is going to be very scale. It needs very highly data consumed. So, and during the search operation, like when you're writing any query or any prompt, the very first operation it does is a vector search. So if the vector search is not gonna scale for your data and not gonna provide the answer in a very quickly, so your AI pipeline that you created is not gonna work. So that's one use case. And the other use case is the database. If we are any analytics pipeline, if we are running, but there were still a question because NVMe-oF using an RBD at the backend, so performance is really at the layer of a baseline is for the RBD. So that's the trade-off. We need to look up that what type of operation we are doing in a database, is it a read operation or is it a write operation. So based on that, we can also use this one also. So finally, conclusion is that with the AI growing, the GPU performance is growing, we need the storage solution which also needs to be fast and cope up with that. So finally, that we need to eliminate the storage bottlenecks and provide very performance storage for your cloud database. Thank you.
Thank you, Kritik. Any questions here from the audience? Please. Wait. Oh. Thank you.
Okay, thank you. Can you go back to slide 35? To slide 35. I have a question about that particular part. Because
which slide?
35. Yeah, benchmarks, yes.
This one?
I have a hard time believing these numbers, because why, if you add an additional layer between the VM, so NVMe-oF fabric is just an additional layer, but it still talks to RBD, how can it improve performance? Because you're just adding more software in the whole path. So I think there's some caching happening somewhere in the NVMe layer when reading.
Yeah, so there is some caching happens because NVMe-oF gateway itself stores having a SPDK, so it also have its own caching internal mechanism. It's there, so that's why when you do search, it's very quickly to respond back.
Okay, but if you would just move this cache to the VM where the workload runs in, so just give the VM more memory, you would get the same results or even better results, but you still run on plain RBD.
RBD is not gonna scale that much because it's RBD depend on the OST Ceph cluster to have that performance. Because RBD is gonna connect directly to the OST to write and do an operation. So OST memory, if you increase, it can. But
no, I mean the VM. If you give the VM more memory, then the page cache of the kernel will just load more contents of the disk into memory. And then the vector database will probably get the same or better performance. Because I was just looking at these numbers, and also the next slide,
this one?
One back, this one,
yeah.
Saying that, yeah, you have a higher search QPS. Okay, yeah, because the NVMe layer caches, I think that's the answer to my question. There's a cache in the NVMe layer.
Yeah.
Okay.
So, any more questions?
I think at the back there is a question.
Sorry, who?
Okay.
No. Okay. All right. So, Kritik Sachdeva, thank you very much for your talk.